Hello everyone, and welcome to this event. Today we're here to discuss the next steps in multi-phase pumping, Leichtritz proprietary HydroCompression Technology. I'm Jeff Duvall, President of Leichtritz Americas, and I'll be joined by my friend and colleague Roland Mareschat, our Vice President of Engineered Solutions. Roland and I have worked together now for over 26 years, devoting most of that time to multi-phase pumping in the upstream oil and gas industry. For those of you unfamiliar with the technology, multi-phase pumps have the ability to handle the full untreated well stream through one piece of rotating equipment. This compared to traditional production methods that require separators, compressors, pumps, flares, surge protectors, and so forth. The most common applications for multi-phase pumps are pressure boosting and wellhead pressure reduction. And there are hundreds of pumps operating globally, both onshore, offshore, topside, or subsea. Based upon positive displacement pump principles, Leichtritz twin-screw multi-phase pumps offer tremendous operational flexibility, especially when used with variable speed drives. This allows operators the ability to use one piece of equipment, even with dynamic field conditions. But it's not just pressure boosting. Pumps are also used for blowdown, annulus gas, hydrate formation mitigation applications. Today, most multi-phase pumps operate with other forms of artificial lift. Multi-phase pumps operating in conjunction with gas lift, sucker rod pumps, PCPs or ESPs offer tremendous efficiency gains for operators as well as incremental production gains. This often leads to the pump paying for itself within a matter of months. However, it's not just about producing more oil and gas. Two overwhelming factors currently drive the direction of this industry. First, there's tremendous political and social pressure placed upon operators to reduce their carbon footprint as well as carbon emissions. And most of you have responded by promising to reduce routine flaring by 2030. Secondly, shareholders and financial institutions are demanding greater fiscal responsibility. This is a shift from production growth to value growth, gaining more from existing infrastructure and extending end-of-life production from existing wells. These trends have led to a surge in demand for high GVF or wet gas compression technologies, especially with light-grade crudes or condensates. This technology must be both scalable and efficient. And this is where hydrocompression comes in. At this time, I'd like to turn it over to Roland, where he can share with you more about the details and developments at Leichtritz. Roland?
Thank you, Jeff. This is exactly why we developed the hydrocompression concept for extremely high gas fractions and for low viscosities. Before we go into details, let's have a look at first how a twin screw pump works in multi-phase applications so that we can really appreciate the changes that we made for the hydrocompression concept. You see in the back here the classical twin screw pump used for multi-phase pumps. The incoming fluid is split into both suction sides of the pump. The screws are transporting it towards the middle, and then the fluid is discharged on the top here. And in the following pictures, we will have a look at the screw section of it to better understand how the compression concept works. What you see here is a rotating screw. The fluid is moved from the right side to the left, and the gas is actually compressed by the backflowing liquid from the discharge side into the pumping chambers. And this is resulting in a relatively low efficiency of the twin screw pumps in high gas fractions. What you see here now is a sketch how a screw compressor works, where the chamber is moved against a fixed wall on the discharge side of the compressor, and only when the screw is reaching a certain point, the gas can discharge. This results in a better efficiency of the screw compressor, but it's also limited to slug flow or high GVF. This machine needs a constantly high gas fraction. With the hydrocompression concept, we combine the two advantages of the screw compressor and the screw pump in one machine. What we replaced is the fixed wall of the screw compressor, and we replaced the fixed wall by the liquid on the discharge side of the pump. And we assume that the inertia of this liquid is high enough not to flow back into the pumping chambers. That means that our pumping chambers are moving the gas towards this liquid, compressing the liquid, and then it can discharge on the discharge side of the pump. This results in a higher efficiency than a classical screw pump, still maintaining the advantages of the tolerance against slug flow or lower GVF flow regimes. So how can this concept be applied to an existing screw pump design? It's fairly easy. We have to reduce the number of pumping chambers. We only need actually one pumping chamber, like a screw compressor. This makes the machine overall shorter. We have to minimize the backflow through the internal clearances. We have a patent pending on minimizing the internal clearances and therefore minimizing the backflow. And we want to increase the speed of the pumping chamber towards the discharge. This would result in a higher compression efficiency. So these changes actually can be made without major changes in the screw pump design. So we can use our proven multi-phase design and include the hydrocompression concept in this existing design. In order to compare the benefits of this hydrocompression concept, we've made a couple of case studies. I want to share one case study with you, which is for an application in Northern Africa. We have a total flow, in this case, of 490,000 barrels per day with a discharge pressure of 500 psi and a suction pressure of about 45 psi. High GVF, 98.5%. And with a classic multi-phase pump, we would be using close to 4,800 horsepower. Using the hydrocompression concept, we would reduce this power requirement by 1,000 horsepower, resulting in 3,800 horsepower for this machine. When you translate that to savings due to energy consumption, you would save about $300,000 US if you would have an electrical drive. And if you want to drive this pump with a diesel engine, you would save more than $600,000 per year just on fuel costs. And with this, I turn back to Jeff for some further comments.
Thank you, Roland, for that great presentation on the hydrocompression technology. Maybe now you could give us a little bit more insight as far as operating windows where the technology is most effective, in particular total equivalent flow rates, GVF, and inlet pressures.
Okay, Jeff. When you look at inlet pressures, that's probably one of the most important things. Inlet pressure should be as low as possible. I was showing in the case study 45 psi. I would say everything from 20 psi up to 200 psi would be a favorable range for inlet pressures. Differential pressures is fairly independent. Flow rates, be careful, I'm talking about now total flow rates. I showed in the case study 480,000 barrels per day or 490,000 barrels per day. This is somewhat the upper range, around 500,000 barrels equivalent per day. The lower end would be in the range of 50,000 barrels per day. So this range would be a good range for hydrocompression. And of course, gas fractions, I would almost say as high as possible, 99%, 98%. You won't see a large effect when you go below 90% of GVF.
All right, fair enough. So with all these efficiency gains from the technology, is there any impact on the system overall?
Sure. In my presentation, I was just talking about the pump itself to make you understand how the pump works. But this hydrocompression concept has also a big influence on the overall system. I indicated already also in this case study that the power requirement can be reduced significantly. I stated there 1,000 horsepower in savings. So your electrical motor could be 1,000 horsepower smaller. Also, if cooling is required, process cooling, then this can be either reduced significantly or even eliminated. And when you look at the auxiliary units like the loop oil system, of course, if you put less power into your pump, into your system, then you also need less cooling on the timing gears and the bearings of the pump.
Okay. All right, fair enough. So when you're talking about the reduction, you said of almost 1,000 horsepower. I mean, can you put that in terms of percentages for like a smaller application? If you're at a 50,000 barrel total flow equivalent, like what the reduction there might look like?
The percentage would be the same. Typically a 50,000 barrels per day pump, I would say, goes around 500 horsepower, 500 to 700 horsepower. So I would also expect a saving of about 20%. That means you would be able to reduce your power requirement by about 150 horsepower per unit.
So that's rather substantial.